Alright, welcome back guys. I'm going to look at these last two examples here. Example 6 is, just like all the others, it does ask us to find the range of this particular function. Okay, and then we're not going to actually have to graph it. Alright, so I'm going to start out in the same way. I'm going to go ahead and try to find the x-coordinate of my vertex. It'll be negative b over 2a. So negative b here is a negative 4. So negative 4 again over 2 times a. Now a here is actually a fraction. It's 1 over 2. Okay, so it's 1/2. Well, a negative 4 is a positive 4. 2 times a half is 1. And 4 divided by 1 is 4. Okay. That'll be the x-coordinate of our vertex. Now we'll find the y-coordinate the same way. We'll just plug 4 into the function. So we'll have, that would be 4 squared over 2 minus 4 times 4 plus 8. And I'm going to do this one in my head. 4 squared is 16 divided by 2 would be 8. With this 8 is 16. And then this here in the middle will be negative 16. So a positive and a negative 16 is actually 0. Okay. Alright, so our axis of symmetry will be x equals 4. Is this function is 0 going to be a maximum or a minimum? Well, what's the orientation of this parabola going to be? A here is a positive. It's a fraction, but it's nonetheless positive. So a is greater than 0. So the orientation will open upward. Okay? And so consequently, we will have a minimum. A minimum of 0, and then we'll say when x is equal to 4. Okay. Now, where is the function increasing and decreasing? Then we'll look at the range. Now, actually, let's look at the range first. We can figure out what the range is without having to graph it, because we know the orientation of the parabola. If this point, the vertex, is right here, that's your low point. Okay? And so remember, the range refers to the range of y-coordinates. So this is, the vertex is 4, 0. So the lowest y-coordinate will be 0, and then the parabola goes up from there. Okay? So the range will go from 0 to positive infinity. But you've got to put a bracket around the 0, because 0 is a function value. Okay, it's included in the set of y function values for this function. Okay. Now, finally, the intervals over where this function is increasing and decreasing. And then we will take a look at the graph just to confirm. Well, again, look at the orientation. It's decreasing first, and then it's increasing second. Okay, so I'll do decreasing first. It's decreasing from negative infinity all the way down here to the vertex, which again, remember, has an x-coordinate of 4. These are with respect to the x-axis. And then from there onward, it's increasing. In other words, from 4 onward to positive infinity, the function is increasing. Okay? And then we can actually graph this. Let's graph it in Desmos. So x squared over 2 minus 4x plus 8. Squared over 2 minus 4x plus 8. And here we go. Look where the vertex is, 4, 0, just like we said it was. So you can see it's decreasing from negative infinity to right here at 4. And then from 4 onward, it's increasing. And furthermore, guys, because it's sitting on top of the x-axis, the range goes from 0 upward, from 0 to positive infinity. Okay? So we did all this without actually looking at the graph of the function. All right. Okay, so, pause the video if you need to. If you're working this out at home, if you've printed these notes and you're working them out, just pause the video. All right, now let's take a look at example 7, the last one. And this is a good example of how you can apply quadratic functions to everyday situations. So it says here that we've got this model rocket, and this could be any projectile. And it's launched with an initial velocity of 100 feet per second from the top of a hill that's 20 feet high. And then it says that the height of the rocket in feet, okay, t seconds after it's been launched is given by this function right here. Let's write this out. S of t, so t is like our x in this example. T, which represents time, which I've mentioned before, in lots of everyday modeling, using functions to model, time is the independent variable. Because so many things depend on time, don't they? And then you'll see this S if you ever take a physics class. We could use F of t if we wanted, but S is typically used to denote the actual position of something in physics. So that's why this function is S of t. So S represents the height. You could also have used an H if you wanted, H of t. And the function itself is negative 16t squared plus 100t plus 20. Okay? And I'm actually going to draw a little visual here. Okay, so let's say this is where the rocket is, and it's launched from a height of 20 feet. Okay, so this is regular ground level over here. So this rocket's going to take off. It's going to shoot way up, and then it's going to fall back down. Okay, it's going to hit the ground somewhere over here. And so what we're trying to figure out, let's read the rest of this. It says, determine the time at which the rocket reaches its maximum height, and then find the maximum height. Okay? So if you're looking at this, this is really just a parabola. And all this boils down to is finding the vertex, because the vertex, or this point up here, represents the t will represent, or the x-coordinate will represent how long it takes to reach that maximum point. And then s, y or s in this case, will represent the actual height, okay, the maximum height. And notice, look at the leading coefficient here. A is a negative 16, which makes sense. Look at the orientation of our parabola. It's upside down, right? Because we're modeling the path of a rocket. There's a couple other things I want you to notice. It said that its initial velocity was 100 feet per second. Well, we see that in here, in the actual function. And furthermore, we say that the rocket's initial height is 20 feet because it's launched from this hill. And we see that in this function as well. Okay? It's already 20 feet above the ground. It's launched at 100 feet per second, and then this negative 16 here, this negative 16 comes from the acceleration due to gravity. Gravity's pulling the rocket back down. So if this function models the height of the rocket, the rocket's height is being influenced by gravity. Gravity's pulling it back down. So it's not going to stay up there forever. It's going to reach a maximum point at the vertex and fall back and hit the ground. Okay. So in other words, guys, you're just simply finding the coordinates of the vertex for this problem. So t, or x, is found by negative b over 2a. So it's the same problem again, right? It's just in context. So negative b in this case would be 100 over 2 times a. A is a negative 16. Okay. So we'll get a negative 100 over, that'll be negative 32. The negatives will divide out. And in the everyday context, you're not going to get nice numbers. You're not going to get a nice number here. 100 divided by 32, let's see what this is. It's 3.125. And this is in seconds, guys, because that's what t represents. So that's what our independent variable in this problem represents. This is the time that it takes to reach the maximum, okay? And then to find that actual maximum height, we need to find s of t, or in other words, s of 3.125. Okay, so we plug the time into the function, and the function will give us the height of the rocket. Because that's what the function is modeling, the rocket's height. And it's a function of time, or it depends on time. Alright, well, I guess I'll go ahead and write all this out. 3.125 squared plus 100 times 3.125 plus 20. Okay. Now you can type all this into your calculator if you want. Let me show you what else you can do with your calculator. You actually type the function in here, and I'll do this. Negative 16. We have to use an x instead of a t. Plus 100 x, and then plus 20. Now I would say you could go and look at the table to find those that corresponding y coordinate, which represents the height. But the table doesn't list a value that's a fraction. Okay. So what you can do, if you come over here to table set, hit second window, you can go down to the independent variable and click on ask. What that will do when you go back to the table is you'll be able to input your own x values, and those corresponding y values will be generated automatically. Okay, so now if I go back to the table, it's just waiting for me to input my x values. So I'm going to input 3.125, and I'll hit enter, and that's what I get. This is the rocket's height after that amount of time. Okay, so you know, if you had to evaluate a function for a lot of different values of x, this might be the way to do it. You can input your own values of x instead of the calculator generating those integer values of x. So anyway, we end up getting, I'll just restate this. S of 1.25 is equal to 176.25. 176.25 feet. Okay, so that answers the question. The maximum height of the rocket is 176.25 feet, and it reaches that height 3 1/8 seconds after it's been launched. Okay, I'm going to go ahead and change my table settings back to automatic. Quit. Let's go ahead and graph this function in Desmos. You can call it S if you want. S is equal to negative 16. Negative 16t squared plus 100t plus 20. Okay. And so look at this. This is a parabola. If I zoom out, just a very thin parabola. Okay. But look at it. Look at where the vertex is right here. Okay. So if you were to look at this, would be like almost the literal path that the rocket would take. Now notice it hits the ground right here. This point right here represents the time that it takes before it hits the ground, so it's about 6.4 seconds. But notice, let me zoom in at this point right here. The y-intercept is right here because it was launched from that heel. Okay, so after after 0 seconds, it has a height of 20. Well, that's just by virtue of from where it's launched. Okay, so really the only piece of the parabola that corresponds to this scenario is from this point all the way up to the maximum and then all the way down to this axis. The rest of it we don't need. The rest of it is not applicable to the context of this problem. The rest of this just shows that if it were to continue at that path, it would just keep going down and down and down. But we know that can't happen because the ground is right here. So anyway, I just wanted to show you that. Just to show you this in context and show you how powerful these quadratic functions can be. Right. And there's a little video that I put in there just showing you some different real-life objects that are parabolic shaped. Okay. Now, let's be clear. The arch in St. Louis, Missouri, that technically is not a parabola. It looks like one, but it's actually another mathematical shape. Okay. So some of those images that you'll see are oversimplifications, but parabolas do occur a lot. Anytime an object's falling, I know there's a lot of pictures of that, then they do fall. They do have parabolic paths. Okay. But anyway, just wanted to make that disclaimer.